So here's a little bit of a lecture. We've done some of this stuff in class, so you can look at the notes, but some things here to help us out. And we discussed some of this last week when we were still in school. So electrostatics things, what kinds of charge are there? Positive and negative. What types of objects allow charges to flow easily? We call those conductors. So those are things like metal and most types of water. And what types of things do not allow charges to flow freely? Those are called insulators, rubber, air if it's dry, plastic, pure or distilled water only. That's the only things you can buy. So almost all water has dissolved solutes in it. So probably don't think of that as a great insulator just because it's the exception. Um, Things you should know about charges related to chemistry. Electrons are negative, they exist on the outside of atoms. Protons, positive, exist on the inside or in the nucleus of atoms. So it's much easier to gain or lose electrons that are on the outside of atoms than it is to gain or lose protons, which are basically the whole atom itself. So in solids, electrons are usually the charge carriers. In liquids, often positive charges can be the charge carriers. Or plasma, which is what the sun's made of, also positive charge carriers. But for us, most of the time we're going to think of electrons as being the charge carriers. So if something is neutral and it becomes negatively charged, it's gained electrons or gained negatives. If something's neutral and it becomes positive, it hasn't gained positives, it's lost electrons or lost negative charges. And we're going to have a simulation or a concept builder that allows you to see that. So what about neutral objects? Objects that are neutral are attracted to either positive or negative objects due to a property called polarization. So that's when a neutral object has separated charges. So for example, if this is a positively charged object, and you can get charging by rubbing things on something else, we demonstrated that in class, then if this allows the charges to flow in it to even some extent, the negatives or opposite charges will be attracted, the positives or like charges will be repelled. Well, since the negative charges are closer to the positive, that's a stronger attractive force than this is as a repulsive force. Again, on Friday, what we did is we saw that with several examples with the Van de Graaff generator. So a neutral object will be attracted to either a positive or a negatively charged object. So that makes it a little tougher to tell. When objects repel, it's always due to positives interacting with positives or negatives interacting with negatives. Opposite charges or a charged object with a neutral object will not repel. So the official unit of charge is called a Coulomb. It's a very large amount of charge. So the fundamental unit of charge on either a single electron or proton contains 1.6 times 10 to the negative 19th coulombs of charge. And so that's something to remember. And these are the conversion factors here. In nature, you can't get smaller than one fundamental charge. So you cannot get less than that on any object. There are some subatomic particles called quarks, which can have partial charges making them up, but they cannot have, in nature again, individual materials or charges can't be less than 1.6 times 10 to the negative 19th coulombs. Charge can build up on insulators, but not on conductors. Why? Because conductors allow electricity to flow. So we saw that on Friday where, there's a little bit of an exception to that, I'm sorry. If we have an isolated conductor like the Van de Graaff, that wasn't touching anything else, they can build up there. But usually insulators allow things to build up, things like a rubber on a balloon, again, things that won't allow it to flow. Why do some objects become positive and others become negative? Normally it's because those objects have interacted with something, with rubbing or friction, and some substances attract negatives more than others due to their chemical structure. So we go back to like valence electrons in the periodic table. The atoms toward the left side of the periodic table have only one or two extra electrons, they're metals, and they tend to want to get rid of them pretty easily. The materials on the right are nonmetals. They want to try to gain some to get a complete octet. But it really just depends on the interactions of any two individual materials. So Physics classroom has a whole section on this called triboelectric series, and we're not going to get into it that much. We did demonstrate things on Friday with the electroscope. So metal ball, metal leaves. The box was made of insulating material. And we showed some demonstrations here with these. So if you touch it directly, since that's metal, the charge is spread out as far as possible. The leaves went apart. For example 2, which we also did, and this is charging by conduction or direct contact. This is induction or indirect contact. So if we bring this close, through polarization, which we talked about a couple pages ago, up here, through polarization, the negatives tend to be attracted up here to these positives, and the positives tend to repel. Again, in reality, there's trillions of positives and negatives in any neutral object. We're just showing the excess, and it's really a sketch. So I don't know exactly how many there are. So, at any rate, like charges repel, opposite charges attract. Temporarily, we get these leaves to go apart a little bit, not as much up here as up here. But then when we remove this stimulus, then everything goes back to neutral. In other words, these negatives don't like to be close to each other if there's nothing causing them to be attracted up to the top. And these positives definitely don't like to be close to each other either. Grounding is when a charged object is discharged by providing a path for the charges to flow. We saw that with a Van de Graaff or with the electroscope. So if we have an initially a negative electroscope with the leaves spread out, they can pass through me to the ground. Neutral. Didn't get a chance to do this. Didn't get a chance to do that. We definitely did Van de Graaff things. I don't think the Millikan oil drop it experiment is that important for what we're doing. But I like my picture. That's a good spray bottle. It could be used for disinfectant these days. So this is important. This is Coulomb's law. And I will attach part of a reading to physics from physics classroom about this. So the force between 2 point charges is represented by Coulomb's law, which takes the following form. Electric force, K, which is a constant, times Q1 times Q2 over the distance squared. And I'll also give you a really good video from a guy called Flippin' Physics about this. So this is a constant, 9 times 10 to the positive 9th. Don't worry too much about the units. It ends up where we get a force here in newtons. Charge 1, Q1 in coulombs. Charge 2, Q2 in coulombs. And R is the distance between the charges in meters. So this really resembles the universal gravitation formula we talked about a month ago. They look very much the same. And that's really characteristic in nature to have something where we have, if we have 2 point sources and they create a field in 3-dimensional space, we're going from 1 dimension, or a point source rather, 1 pinpoint, to 3-dimensional space. We're really decreasing by 2 dimensions. And so that's why it's divided by r squared. It gets very weak very quickly. So the force between these charges can be either attractive or repulsive, depending on whether Q1 and Q2 are positive or negative. Same rules of forces still apply in terms of Newton's laws. So Newton's second law still works, and Cole-Johnson, your favorite law, Newton's third law, also works. So even if one of these charges is much more than the other, the force interacting between them would be the same. So any charge creates an electric field around it, just as how any object with mass creates a gravitational field. A uniform electric field, the field strength is simply a ratio of force to charge, newtons per coulomb. Notice that that's really similar to a uniform gravitational field, such as on Earth when we think of G, which we can think of as a gravitational field strength. Sometimes we think of it as acceleration, which is meters per second squared. Sometimes we think of it as newtons per kilogram, which is actually how we thought about it at first. By convention, gravitational field lines point toward an object with the largest mass. By convention, electric field lines point from positives to negatives. Again, I don't think we're going to deal much with this, but I want to make sure you saw it and see the analogy. We don't always have a uniform gravitation field. We don't always have a uniform electric field either. Big idea here is if you have a point source, substitute in Coulomb's law, you show that from away from a point source, these arrows get further and further apart, so the electric field gets weaker and weaker. This formula is not that important. I just want you to understand it's a non-uniform electric field. It gets weaker as you go further away from the source. So observations about a charged conductor. Excess charges will always lie on a surface. So the excess charges on the Van de Graaff are on the outside of the Van de Graaff. There's no difference in energy of the charges on the surface. That means it's equal energy. If there was a difference, they would push each other to a different spot immediately, pretty much, because it's a conductor. 3 and 4, not super important. If we had a sphere, the charges would spread out evenly. If we have a weird shaped one, like this is like, I guess, an avocado shape, the charges tend to accumulate close to a point. And that's why on Friday, what we noticed was a pointy object will allow charges to disperse on it quickly without building up to enough to cause a shock. So when people were on the Van de Graaff, I put my keys up to them, which was a pointy metal source. You could hear the charge leaking out. Big ideas overall as a recap. Potential difference, which is a difference in energy per charge, is called voltage. This deals with electrostatics things, and we'll talk about it with circuits. A potential difference or a voltage difference between two objects can cause charges to move. As charges lose voltage, they convert electrical energy to kinetic energy as motion or heat. And these are not that important for what we're going to talk about right now. So we did have the plasma ball or a sunder ball and a fluorescent light. Hope you like that. It showed that there was higher energy toward the center and less toward the end. So the fluorescent light lit up even though it was not directly touching the ball. And I think that's it. So hopefully that'll be good.